Right, okay, so this was D to G. Right, one of the things that I'm going to get really, and you might think I'm being petty or narky, and really that's up to you, I don't care. I'm going to get really picky about clarity, okay, and making things clear. You are aiming this at somebody, eventually, hopefully, at an exam board who is being paid under extreme pressure to get results in the computer quick as possible, probably not very familiar with the subject anyway, okay, judging from the conversations that I have online with people who, one minute they're asking for help on something and you're thinking, why don't you understand that? The next minute they're telling you they're doing exam marking. And it scares the bejeebers out of me. And I'm not making that up. So you have got to be ultra clear. You have got to try, and it's not always easy, but try and deliver answers that flow, okay, and have definitive conclusions. So this is the answer. Here is a load of working. In an ideal world, you'd have time to annotate your working to explain what the hell all these random numbers are. Okay? Particularly important when you're doing all that floating point stuff, because you end up with loads of noughts and ones all over the shop. Alright, so in an ideal world, that's what you would do. If, for instance, at the end of an exam you had 10-15 minutes, I would go back and I would annotate a few bits. If I was happy with what I'd written. Just to make sure that I'm giving the person at the other end the best chance to award me the marks that I deserve. Okay? If something's not clear, then the chances are it won't get marked properly. Not because the examiner's been lazy, but they haven't, I don't know what the hell you mean. They can't phone you up and say, oh, what did you mean when you wrote all that squiggle? Alright, so I'm going to get mean about clarity. If something's not clear, I might actually, if something's very not clear, I did with a few people on this, didn't bother even marking it. So, no, sorry, that's not good enough. Alright? It's particularly important with Dijkstra and A-star with the columns. Don't make your own names up. It's an algorithm. You can't start calling the heuristic column the cat column. I think someone had cost 1, cost 2 and final cost. Or total or something like that. And it was like, right, okay, don't know what algorithm you're following. And neither would the examiner. They wouldn't be able to tie that up. You're making them imply what the columns are. Can't do that. Right, okay, so this first one was Dijkstra. D to G. So this is a search. We're going to stop when we visit the G node. Okay, but we want to make this clear for the examiner. So we're going to have some columns. We're going to have a node column. We're going to have a cost. We need to leave a little bit of a gap after cost because we might have to update costs. Okay, so I'm going to leave a little bit of a gap and I'm going to put my parent there. Right, the clear thing, I'm just going to list all my nodes to start with. I noticed some people did them as they approach them, but actually with Dijkstra, every node is made available to search to start with. So I'm just going to list them. I've got A, B, C, D, E, F, G. Right. The only one that we have a definitive idea about the cost is the start node. And that will have a cost of 0 because we haven't moved anywhere. Alright, so we always put that in. The others, Dijkstra is agnostic. It doesn't know anything about where the goal is. It knows what the goal it's looking for, but it has no idea about its relationship with the start point. So it assumes that every node is going to cost an infinite amount of travel cost. So we put infinities in. I noticed, I can't remember what it was, someone put infinities in for A star, so that shows they weren't using the right algorithm. Straight off. And really, the root, nobody's saying, can you tell me the root? Because you can see it. You're a human. You can see the entire graph. You can work the root out without using any algorithm. All right? So that's only a one throwaway mark. The meat of these questions is always about demonstrating your understanding of an algorithm. Okay? Right. So there is only one process. Start it off, and we do that by fixing the cost for Dijkstra's start node as 0. And then there is the iteration. And the iteration is just pick out the cheapest cost. If it's the goal, stop. If it isn't, let's have a look at how much it's going to cost to reach the neighbours of this node, if they have not already been visited, and update any costs. That's all we do. And we just keep going. Okay? Right. So initially, our first iteration makes us pick D. So we're going to do a number just to indicate that that was the first pick. This, I think, is important. I didn't used to get students to do this, but the way that the mark schemes are starting to be written, they're being written in student picks this one first, then they look at this one, and you think, well, how are you going to demonstrate that to the examiner without labelling it up? All right. The other thing that I've been doing tons of these lately because I've set a load for year 13, and obviously I have to work through them all. But what I've also been doing is I've been putting a little X so that I don't ever update that row again, because I'm not allowed. Once I've visited a node, I can't update any costs because it's not available. Right, so I'm just putting those two markers in. There is no parent for D, so I'm just going to put a null marker, just like a hyphen or something. You can write null if you want. We tend to put a hyphen. And I'm going to look at its neighbours. All right, so I can see I've got two neighbours, B and F. Currently, they cost an infinite amount. So Dijkstra will always force you to update nodes at least once. Okay, because they'll start with these infinities. So we look at B. Let's look at that one first. It's got a cost of travel of 5. So it's going to cost me 5 to get from D to B. But to work out what the cost to B in total is, I have to look at how much it's cost me to get to the node I just picked. Well, actually, because it's a start, it's a 0. So the full cost for B is going to be 5. And that is from parent D. Okay, everyone happy with that? It's a bit weird when you first start because there's nothing to add. So you can actually start making the mistake of never adding on the travel cost. So that is one mistake to watch out for. Right, the other one is F. So that's got a costing of 8 on that line that's joining the two nodes. But it only cost me 0 to start. So it's only in total going to cost me 8 to travel to F from D. Okay, and that's the end of my iteration. So I now just go around and pick the cheapest. Super important that you've been really clear with how you've written your table out, otherwise you will accidentally pick the wrong number. So I'm looking at my open values and I've got lots of infinities, so I'm not going to pick those, but I've got a 5 and an 8. 5 is obviously smaller, so that's going to be my second pick, B. So what I do is I look at my neighbours. Now B's got 3 neighbours, A, C and D. But D has already gone. We visited D, we can see that because I've got a 1 next to it and I've put an X to say don't update that anymore. Right, so D we ignore. The other neighbours are A and C. So let's just do A first. So it's going to cost me 4 to travel from B to A. But B has already cost me 5. So I'm actually on a 5 already at B. To get to A is going to cost me another 4. So that's going to be 9. But that is better than infinity, so we're going to update that. And we need to put the parent in, so the parent was B. I think most of you, when I marked this, even if you cocked up the numbers, which some of you did, you did get the parents. So you were doing that bit and then just messing up arithmetic. You don't get a calculator in your exam, so you've got to be able to add up. Okay, so we've updated A. Let's update C. You can see that the cost from B to C is 6. So with the cost that B's already incurred, which is 5, that means that's going to be 11. But that is better than infinity. So I'm going to put that down. So that was from parent B. There aren't any more neighbours, so I've finished the iteration. Okay, so I'm now going to go in the pick again. So I'm looking at my numbers. I've got 9, 11 and 8. 8 is the smallest, so I'm going to pick F as my third pick. Right, F has got 3 neighbours. D, which is gone, it's been visited already, so that's closed off. It's got another neighbour G, which we know is the goal, but we haven't picked it yet. So we're not going to stop, we're just updating travel costs. So let's do that one first. So it's going to cost me 10 to get from F to G. But F has already cost 8. So that means to get from F to G would cost a total of 18. So that is from parent F. We haven't visited G yet. All we've done is we've worked out some costing. We don't know whether there's a better route. There might be a whole bunch of graph that we haven't visited yet. Okay, so the other neighbour is C. Now, C we've actually done a calculation on. We've got a cost from B. But let's see if the cost from F's cheaper. So F to C is 7. F's already cost me 8. So that's 15. No, that's not better. All right? So it isn't better, that cost, so there is nothing to update. No more neighbours, finished my iteration. So I'm going to go on the hunt now for the cheapest cost. Yes?
Will there ever be a time in the exam where you have to say like which ones you haven't updated? Like, so if you, for instance, because 15 was more...
Yeah, what annoys me is in the mark scheme it says that. So it says, oh, this was more, don't update. But you've implied that by not updating it, haven't you? And you can see that I've visited number 3 was F. So I don't know. How much can you be expected to write for a 6-mark question? In these take long enough, these are tricky. They're really easy to cock up. They're easy to do, but they're easy to cock up. All right? So if it is one of those things that if you had time at the end, maybe do that and say like, yeah, don't update. Just put a little annotation underneath. So when I visited F, I could see that C was it was a more expensive route, didn't update. But I wouldn't worry about that too much. I think the ordering is important, and the tracking of the ones that have changed is more important. So that shows that you understand the algorithm. Okay, but you can do it for yourself. Harry, there's nothing to stop you doing it for yourself. All right. Right. Okay. So now I've completely lost where I got to, but luckily I can see that I know I've just done an update, and all I'm going to do is look for the cheapest cost. So I've got a 9. I've got an 11 and an 18. So I'm going to pick the A. So that's my 4th pick. Right, looking at my neighbours, I've got B, but B's been visited, so I'm not going to update that. And I haven't stuck to my own little rule there of putting the little X's on, so let's just do that. The reason I haven't stuck to that rule is I haven't embedded it in my head, because I haven't done enough of these. Although I feel like I've done enough over the last few weeks. But the thing with most processors, whatever you're learning, unless you have done it loads of times, you won't nail it down to be automatic. So you have to practice all this stuff. Right, okay, so I'm looking at A. So we've got a node B, but that's closed. So I can't update that even if I wanted to. I've got a node C. That is actually still available. It's still open. So let's have a look how much it's going to cost. So it only costs 1 to travel from A to C. It cost me 9 already to get to A. So that's a total cost of 10, which is better. So that's going to get updated. Now I saw a few of you were doing like square brackets round. That's not a bad thing to do. I'm just underlining. I'm going against crossing through, because as soon as you cross through, you're starting to make it difficult to read. Bearing in mind these are scanned on a machine as well, so who knows what sort of naff screen quality they've got. So I'm just underlining it to show that it's been replaced. Right, so I've got a new cost of 10, and that is a parent A. So B has been bettered by A. Okay. My other neighbour is E, which hasn't been updated. It's still on infinity, this one. So this is going to need to be updated. So it's going to cost me 5 to get from A to E. A has currently cost 9, so that makes it 14. So I'm going to update E with 14, parent A. No more neighbours. So we've visited 4 nodes so far. Let's pick another one. So we've got 10, 14 and 18. So we're going to pick C. Okay, so C is going to be my 5th pick. Right, looking at my neighbours, connected to quite a few here. A, B and F, they've all been visited, so we're not going to update those. But E hasn't. So let's have a look here. So, it only costs 4 to travel from C to E. Right, C has currently cost me 10. So that would mean a total cost of 14. Is that better than the cost we've got there? No, it's not better. So we don't update. All right? There's no need to update unless it's better. So that just gets left. There aren't any more neighbours to explore for C. So we're going to move on and we're going to do a new pick. So you can see that we've got 2 left, 14 and 18. So 14 is going to get picked, which is E. So looking at E, it's got 3 neighbours, A, C and G. A and C have already been visited, so they can't be updated. But G's up for grabs. So let's have a look. So it's only going to cost me 2 to go from E to G. Currently it's cost me 14, so that's 16. That's a better route. So I'm going to update that, and I'm going to say, sorry, F, you look like you were favoured, but E is a better route. Again, I haven't visited G, so do not stop yet. Okay, no more neighbours. There is only one thing left to pick. So that's the 16. So the 7th pick is G. I don't have to do anything. I've found where I'm going. It's a search. A search generally stops when we find what we're looking for. So we're going to stop at that point. We're going to write the G and we're going to work backwards through the parents. So G came from E. E came from A. Now where you write the parent is up to you. It probably is easier if the parent is closer to the node column. You know, you could put node parent or something like that. It's up to you how you do this. Do what's easier for you, because I'm having to like look across the whole table to find the parent. Right, so I've got to A. A was coming from B. B. What you must never do is look at the graph and try and do it from the graph. Do it from your data. All right? Because if you start looking back at the graph, you'll make mistakes. Right, so B came from D, which was our start. And we know it's the start because it hasn't got a parent. Okay? Anyone got any queries about that? They'll probably, it's not necessarily easy to do, but they will generally have a graph that makes you update a node at least once. Okay, when I did the A star one, I managed to actually get a couple of updates in there. All right, but it wasn't easy to do. You have to fiddle about for ages. So I can imagine the process that goes on for people not wanting to spend ages fiddling about. Right, okay, A star. A star isn't really any more difficult than the old Dijkstra, but there's more data to worry about. Okay, so the A star. Right, I can't see my question, but I can see what the goal is. Because all I've got to do is look at the heuristics. The heuristic is the estimate. And it is an estimate of the travel cost from one particular node to the very end. Okay? Do not be fooled by geographical layout. This is an abstract diagram. When generally not always told what these represent. Okay? They may actually be purely abstract. Sometimes they'll have like a map or something like that. But it doesn't necessarily mean distance. I think we've had a question before where they had airplanes. And it was a cost, and it wasn't distance, it was like fuel cost. Based on wind conditions. You know, flying into the wind, you burn more fuel, that sort of thing. But hey, so we just raw look at the numbers. So I can see that E is where I'm going to. I remember now that I think it was A to E, this one, wasn't it? Okay, so it's going to be A to E. So hopefully, when I actually get my route will start at A and end with E. So double check. There were a few people who ended up with a route that stopped before he got to the goal. I don't know how that happened. Check. Right, okay, so we've got the same sort of basic structure. We're going to have the node, but then we've got all these costs. We've got the G cost, which is our travel cost. So we're going to have a column for G. Do not change the names of these. We have, and G could change. G, if we update, is going to change. So leave a bit of space. A few people got into a bit of stum and run out of space, and then that starts getting hideous. So I'm going to leave a bit of space. Then I'm going to put my H. The heuristic is fixed at the start. So we don't need a load of space for that, and we can write all those heuristic values straight in. And then the final cost, okay, the thing that is a combination of G plus H, that will change as we update. So as we get a cheaper travel cost, a G cost, F will change, obviously. And we want the parent as well. So, and the parents will change. So we need a little bit of space for G, F and P columns. Right, the difference, one of the differences between A star and Dijkstra is we add our nodes to our table as we encounter them. We don't need to process the entire graph first. Dijkstra sort of does. We've got to calculate the heuristics, but there may be another mechanical way of doing that. Right, so all I'm going to put on is my start node to start with, which was A. The G cost, the travel cost, we haven't gone anywhere, so that's going to be 0. The heuristic is in the diagram. So I'm going to do this in the way that I would implement it if I was coding it. So I'm going to put my heuristic down. So I'm estimating that it's going to cost 30 to get from A to E. So my full cost is those two numbers added together. It is the F column that you are looking at when you're deciding what node to pick on your visit. Right, the parent of that was nothing. It was the start. Right, the algorithm works in the same way as Dijkstra. You look for the cheapest and you mark it as visited and you look at its neighbours. Update if necessary, or add them in this case. Right, so I'm going to make my first pick. The first pick is quick because there's only one node to pick. So I'm going to mark A as number 1. I'm going to look at my neighbours. Now you've got lots of numbers here and it's very easy to mess up. So I'm going to add, just going to put the two nodes down. So I've got B as a neighbour and I've got G as a neighbour. No other neighbours. They're not connected. Right, I'm going to work on them one at a time, so I'm going to do B first. So, the cost to get to B from A is the travel cost that's indicated, which is 7. Okay, so I've got 7, and whatever it cost me to get to A, which, because it's the start, was 0. So the G cost is 7. The heuristic, which is next to the node, is 20. So let's write down H as 20. So my full cost, the F column, is 27. and that was from parent A. Right, looking at G. G is going to cost me 6 plus the cost to A, which is 0. So the G cost for G is 6. The heuristic says it's going to cost 22 to get from G to the goal. So let's put that down. And we'll do our calculation. So overall, the full cost, as determined by the heuristic, is 28. Now, do not be surprised when you do A star that they've given you a wonky heuristic. I've done it on this one on purpose, so that you do not get the optimum route. This will not give you the optimum route. There is a better route, but A star is told to do, is guided by the heuristic. It's a bloodhound algorithm. Okay, it knows something about the relationship of nodes in the graph. So it's going to use it to make the search quicker. And the trade-off is, it might not necessarily be optimal. Dijkstra will always be optimal. Right, okay, so we've updated that one. Just got to finish off by putting our parent in. Okay, and now we just go back round and we pick the cheapest cost. So ignore the G column completely. Look at your F column. You can see that B is going to get picked next, because it's 27. Okay, so I'm going to try and do my little marker thing. So A was closed off and B is closed off. Right, okay, what are my neighbours? I've got 2 neighbours, so I'm going to add them to my graph because I haven't seen them yet. So I've got C and I've got H. Right, so let's work on C first. So it's going to cost me 11 to move from B to C. Right, it's already cost me 7. So the overall cost via B is going to be 18. Right, the heuristic for C is saying it's going to cost you 23 to get from C to E. So let's put the heuristic in. Now we can calculate the full cost, which is a couple of hideous numbers for me. I don't know about you personally, but I don't like numbers like this. I think that's 41. And that was travelling from B as a parent. Okay. Right, next one is H. So looking at my graph, I can see that it's going to cost me 12 to travel from B to H. It's already cost me 7. So the G cost to H will be 19. The heuristic is saying 19 as well. Now, because I used to play darts quite a lot, I know that that's 38. I can't add it up, but I just know it's 38 from the parent B. It doesn't matter what system you've got for arithmetic, as long as it works for you. Okay, no more neighbours to explore. So we're now going to go around and find the cheapest F cost. This time it's G, 28. So I'm going to mark that off as don't update, put it down as the 3rd pick. Right, neighbours of G. We've got A, that's gone, we've visited that. We've got F, we haven't seen F, and we've got H. So let's add F to our table, because we haven't seen that yet. But H is open, where we can update it if the costing's better. So let's have a look at this. Lots of big numbers here, so we have to be careful. Right, it's costing me 12 to travel from G to H. To get to G already was 6. So 6 plus 12 is 18. Ooh, that's better than what we've currently got. We had 19. So let's update this. So I'm just going to do my little underscore, and I'm going to put 18. Right, so I've now got to recalculate the full cost, so that's 18 plus 19. Well, luckily I don't have to do any arithmetic there because it's just 1 less. So I'm just going to put 37. And that was a different parent, so that was G. So lots to update there. Just take it carefully and logically. Right, let's do F, because F's got no calculation yet. So G to F is going to cost me 7. It's already cost me 6. so 7 and 6 is another one of those numbers I don't like. 13, I think. The heuristic is saying that F is only going to cost 12 to get all the way to E. So let's put the heuristic in. Now we can do our F cost calculation. So that's 13 plus 12, that's going to give me 25. And that was from parent G. Okay, so we've got 3 things to pick from on the next iteration. So the next iteration is saying, oh, we better pick F then, because that's 25. So I'm going to pick F. I'm going to just close it off and mark it down as 4th pick. Okay, let's have a look at F. He's got a neighbour G, but that's gone. He's got a neighbour H. Damn H. Because it's right in the middle, it's connected to a lot of things, so we're going to keep looking at this. Right, so let's have a look. Let's see what it's going to cost us, travelling from F to H. So it's only got a cost of 4. So it's only going to cost me 4. What did it cost me to get to F? 13. So 13 plus 4, 17. That is better than the current cost. So I'm going to update H again. So it's only going to cost me 17. And again, luckily that's just a decrement. So I'm going to put 36. So we've gone through 3 different parents. Hopefully we've found the cheapest route to H there, so we don't have to keep updating that, because I'm going to end up scrolling my page. Okay, so there are no other neighbours to update from F. So let's go around and pick a new node. So we're looking at the F. So you can see Sado C isn't going to get looked at again, because he's got a big old cost he has. Let's pick H, because it's 36. So I'm going to just mark that off and don't update ever again. 5th pick. Right, looking at H, connected to lots of things, but let's just take this logically. It's connected to F, but that's already been visited, so ignore. It's connected to G, already been visited, so ignore. Connected to B, already been visited. But look, there's 2 more nodes here. D we haven't seen, so let's add it to our table. E we haven't seen, so let's add it to our table. It is the goal, but we haven't visited it yet, so do not get ahead of yourself. Right, let's work on D then. So H to D is going to cost me 3. It's already cost me 17 to get to H. So that's going to be 20 as my travel cost. That's what the G column is, remember, travel cost. Travel cost so far. Okay, so the heuristic for D says 7. So let's put the H column in. The total cost, the F cost, is going to be 27. And that is travelling from parent H. Okay, let's have a look at E. Now, so E is going to cost 11 to travel from H. Now look at the heuristic here. The heuristic is rubbish. The heuristic's saying it's going to cost me 19. And it's like, whoa, it ain't, is it? It says 11. But that's the heuristic for you. All right? It's a good example of the heuristic. So it's going to cost me 11. It's already cost me 17, so I've got to add that together. So that's 38. 38. 28. Is that 28? Not 38. No, 28. Now, the H cost is 0. Because it's the end. So there is no, we don't have to guess that one, we know it's 0. So when we do the F cost, it's 28. What you'll find is there will actually only be like 1s and 2s different, so you have to make sure you have calculated these right, otherwise you will screw it up. Right, the parent for E was H with that cost. Okay, we have got 3 things left that we can pick from. So let's do another search of the F costings. We've got a 41, a 27 and a 28. So 27 is the cheapest. So let's pick D. Let's pick 6. Right, neighbours of D. It's got 3 neighbours. E is open, so we can look at that one. H is closed, so we can ignore that. But it's also got C. So let's have a look at C first. Right, so D to C costs 10. We've already spent 20 getting to D. So that would be 30. That is not better than what C currently costs. C was only 18, so there's no updating to do there. Let's have a look at this E fellow. Right, so it's going to cost me 6 to get from D to E. So that's 6 plus 20, which is what my current cost to D is. So that makes 26. That is better than the cost we've already worked out. So 26. Right, calculating the F cost again. Obviously that's quite easy because we're adding 0. So the full cost is 26. So H is superseded by D as a better route. Okay, we've got 2 items left. Let's go around and pick the cheapest again. So can you see how this diagram, this little table starts getting full of numbers? It's really easy to get number blind. Unfortunately, you can't use highlighters or different colours because of the way that they scan the papers. Why they can't scan the papers in colour? They don't print them out anymore. They do them on screen. So I don't, but yeah, I understand people start using silly gel pens and things, which probably won't get picked up by the CCD. So we have to use black. So you've got to use some sort of marking scheme. So yeah, putting square brackets around things, that's not a bad idea. Underlines is not a bad idea. Whatever works for you. Right, so I've got 41 and I've got 26. I'm going to pick 26. That's my 7th pick. It's the goal, so I'm stopping. So I'm going to write down E, and I'm going to say, where did you come from at E? So E came from D. Then I'm going to say, where did you come from, D? So D, and remember I've added these as I visited them, so they're not in any sensible order. D came from H. Where did you come from, H? Let's go back and find H. On this massive list of data, F appears to be where I came from. So where did F come from? So looking at F came from G. Where did G come from? G, right up there. That came from A. Where did A come from? No one. It was the Immaculate Conception and birth. Right, so that's my final route. But I am going to do that. I'm going to underline it and I'm going to say roots. I am not going to let the examiner guess what random string of data is the root. Yes, please. It is a root. It's not necessarily the cheapest. It probably is in this diagram. Don't know. No, because you're looking at the F cost all the time. So there's a combination of the heuristic and the travel cost.
Because I wrote that through as well, but I thought that's what the quick string is the most.
I don't know. It doesn't matter how many nodes. Generally, if you're doing this for real, Grace, in a real scenario, they're probably, like you're just saying, oh, you went through loads of nodes. There may be a cost to visit a node. When we're doing this in like games and maps and things, sometimes you'll say a route might be preferred if it's straighter because there isn't a line. If you're driving a car, you might have to slow down to turn and things like that. But you'd build all that into the heuristics.
So I wrote ADHD, but then I also wrote that one, but I thought that was more like guiding.
Your real core job is algorithm in head, follow the data. Even if you don't agree with the data, it may be they've jigged the heuristic on purpose. We will do more of these later on, but I will tend to, on the A stars, give you wonky heuristics to force the route to like, whoa, that's not right, but it's what the algorithm will pick. All right. Right, okay. Moving on. Are we all right so far? Right. What node did I do for the two? Was it A? Was it the A node for the depth and breadth? It was, wasn't it? Yeah, they were both A, weren't they? Right. Okay. Breadth and depth search. Right. I'm trying to get you to be familiar with the process and then using a queue and a stack. A, because it's a reinforcement of how queues and stacks work. But B, it means you've only got to remember one algorithm. And just flick the data structure over. Right, so in general, if you was to ask what are the overall aims of these two search algorithms, the depth and the breadth, the depth search aims to explore to the end of a graph before exploring another part of the graph. Okay, so it will always, when you do your visiting order, you'll see that, don't worry about what order they got visited, but you will see that you go all the way to the end and then you pick another route to go all the way to the end. With the breadth first, it's more of a layering. So it's like, oh, what are the next set of connected nodes? What are the next set of connected nodes? All right, so they have different uses. The depth one is good for building mazes. The breadth one is really good for storing moves, possible moves from a position in a game. Okay, if you're playing chess, you might do a breadth first search to see what moves could I make, what position would the board be in 4 moves time. That becomes a humongous search. The graph gets huge, really quick. Just looking ahead. It's why I don't bother playing chess, because I can't even be bothered to look ahead one move. I'd rather just randomly pick a move. Drafts is more my game, although you need to look ahead on that as well. But anyway, right, so let's do the depth one first. So the depth one uses a stack. Okay? And whenever we do anything where we're following a stack, whenever we remove something from a stack, we're going to draw a clean stack. Okay? The process starts by putting our start node onto the stack. So let's draw a little stack. I'm going to do it with a little line to mark the base of the stack. So I'm going to start at A, so I'm going to push that on. The nice thing about using the stack and visually doing it, you will get a double check, so you can go back to make sure you have not messed it up. Yeah. I'm doing the depth one first. I'm doing question 4 first, because I said the word depth. So I'm doing the depth first, which is strange because that's what it's called, depth first search. Right. So I start the process off a little bit like what A-Stone Dykes does. They set it up. They set the game up ready for the iteration to happen. So I'm going to iterate. I'm going to pop the stack. So I'm popping A. So I'll write that down. And I'm just going to annotate this for the examiner. I'm going to say visited and the order. And that's what I'm going to write my answer. So A is gone down first. Right, I'm looking at neighbours. It's a graph. So graphs are always about looking at neighbours. So we look at our neighbours. We have got F, C and B. We're going to put them on alphabetically. So I've taken something off the stack, so I'm going to redraw the stack. It's empty currently. So I'm going to push B, I'm going to push C, and I'm going to push F. No more neighbours to add. Unless you've redrawn your graph and done it with one key. Right, I'm now going to pop. That's the start of my iteration, is to pop. So I'm going to pop F. And I'm going to write it down. Just visited F. I'm going to look at my graph. I'm going to redraw my stack, because I've just taken some off and I want it to be clean, ready for the next push. Right, so I go, okay, what neighbours have we got? A. Oh, I've seen A. Ignore it. I have got another one, L though. So let's push L onto the stack. No more neighbours. Let's start another iteration. So we're going to pop. So we're going to pop L. We're going to redraw our stack so it's clean. So can you see, even now, we have visited to the extent of one of the graph arms. Okay, we got all the way down to L, which was the end. No more neighbours. So now, what the stack's going to do is get us to backtrack. Saying, okay, where else could you have gone from A? which is what it's saying to us. So we pop the C. And we say, all right, what neighbours have you got? Well, it's got a neighbour A, but we've seen A, so we're not going to put that on. You can sometimes put things that you haven't visited specifically back on to the data structure, but that's for special cases. We're interested in just purely visiting them all once. So if we've seen something, we don't put it back on the stack. So A will not go on the stack. I've just popped the C, so I'm going to redraw a clean stack. So it's just got B on it. Right, C's also got a neighbour E, which we haven't seen yet, so let's push that on the stack. That's it, no more neighbours for it. Right, I'm going to go back round, iterate, so I'm going to pop, write that down, and then I'm going to look, what neighbours have I got? I'm going to write my stack out again, ready for my neighbours to go on. So I've just got B on there, so B's been sat on there for ages, the nature of a stack. Okay, right, E has got a neighbour B, but we've already seen B, so we're not going to put it on again. It's got a neighbour C, but we've seen C. But it has got two more neighbours, H and K. So let's push them alphabetically. So H, then K. It is not a shame to write a alphabet line out if you're doing something critical. It's not. You might get a little chuckle from the examiner, but if you got the question right, who cares? Just the same as if you're doing hex and you desperately don't want to screw up a hex question, so write A, B, C, D, E, F. You'd be surprised how many people screw up, especially the odd numbers. Right, okay, so I've added my neighbours. Let's pop. K comes off. K has got no neighbours that we haven't seen. So I'm going to draw my stack. So it's nice and clean, ready for the next iteration. So there were no neighbours, so it's going to pop again. So we pop the H. Let's redraw the stack so it's nice and clean. Right, neighbours of H. It's got a neighbour E, but we've seen E. But it has got a new neighbour, G. So let's push G. No more neighbours. Let's pop and start another iteration. So we pop G. Okay, let's redraw the stack so it's nice and clean. Just got B on it. Nearly getting to B. Right, G has got a neighbour. It's got three neighbours. H, which we've seen. B, which we've seen, sat there on the stack, crying. And D, which is new, so let's push it. No more neighbours. Let's start another iteration by popping the stack. So we end up with D. D has got no neighbours that we have not seen already. So we're going to redraw our stack. And we're going to pop B. So we pop B. B, because he's been sat on there all day, has got no neighbours that we haven't seen already. So that is now an empty stack. Yes, come. The pure ordering. Pure. Generally, Callum, with a question like that, there are actually 3 or 4 different ways in which you could actually process it yourselves. You can do it graphically if you wanted, or you could use your finger. So really, they're only ever going to say, did you get it in the right order? No. The working out is for you, because you're following the algorithm out. The Dijkstra and the A star, you'll always get marks for the working out. This is sort of like the opposite. This is like the only thing that really matters is the node order. All right. So yeah, if your node order went awry, then bleh. All right. Okay, so that was the depth. Let's do the breadth. Right, breadth's a little bit easier to do because it's a queue, and queues are generally easier to mess with. So again, we start the process by putting onto the queue the start node. So we're going to on queue A. So to do a queue, I'm going to do like a rectangle. I'm not going to try and put separate containers for everything. I'm just going to do that. The interesting thing about this one, the queue as it is will be your solution. Okay, so still write down your nodes cleanly. So I'm going to set up this visited order, or a W there, visited order. But the queue is there for me to do my working out and for me to annotate things. Right, so I'm going to on queue A to start the whole process. So we dequeue. So I'm going to mark that by just putting an X. I'm just going to write, that is not in the queue now. But I'm going to write it down. It's been visited. I'll look at my neighbours. My neighbours, C, B and F. I need to add them to the queue. So I was told in the question to do it alphabetically. So I'm going to go B, C, F. That's it. Just going to go and keep iterating doing that. So dequeue, write it down, look for neighbours. Right, neighbours of B. A we've seen, G we haven't, E we haven't. Let's add them alphabetically. So E and G. Process to neighbours, so let's just iterate by removing, dequeuing the C. Look for the neighbours of C. Right, C has got a neighbour A, we've seen it. It's got a neighbour E, we've seen it. Nothing to add. So that was a quick iteration. So let's iterate by dequeuing again. F. Right, F has got a neighbour A, but we've seen it. Aha, it's got a new neighbour L, so let's add L. Okay, we're going to iterate again. So let's dequeue. We remove from the Q and E, and we look at its neighbours. It's got a neighbour C, but we've seen that. It's got a neighbour B, we've seen that. It's got a neighbour H and a neighbour K that we haven't seen. So let's put them into the queue, on queue them alphabetically. H before K. Right, iterate again. Take G from the queue. Right, neighbours of G. Oh, B, seen it. H, we've seen it. But we have got a new one there, D. Right, let's iterate again and dequeue. So L comes off. L has got no neighbours we have not seen. So nothing to do. Let's just dequeue. H. H has got no neighbours we have not seen. So let's iterate again. Dequeue. K. K has got no neighbours we have not seen. So let's just iterate again. D. D has got no neighbours we have not seen. That queue is now empty. Iteration stops. So that is my order. So you can see, actually, as you built the queue up, the queue gives you the order you visited. But you can see it's done it by layers. So we did A first, then we did B, C, F. Then we did the next level out, which was G, L, and E. Then the very final level was H, K, and D. So there was 3 moves to get to those. So they're both really good systems. Clever little algorithms. So simple, yet they can navigate such complicated data structures. Amazing. Right, okay. So the next question was post-order traversal of a tree. And in this case, an ordered tree. Right. There is an algorithm for this, but there is a graphical way of doing it, which is simple. And that's to do a post cut of each node. Post means after. Okay? So what we do is we get a pen and we go near the center of each node and we draw a line going to the right. And we just do that for each node. So that's the setup. So this is post, as in after. So I'm just going to mark all my nodes. Most of you did this bang on. Some of you did it in the middle. Obviously that didn't work. You did the right process, you just set it up wrong. Right, okay, so all we then do is we walk around the tree anti-clockwise from the root. So we go to the top of the root and we walk, and we want to hug the branches of the tree. It's really important to tree hug, otherwise you will jump a gap in the tree. So I'm going to stay as close as I can without scrolling all over the diagram. So, staying close. I'm staying close to those branches. As soon as I cut a line, I write it down. And again, I'm going to mark it for the examiner. This is the order I visited. So visited order. Right, and I'm just going to keep following those branches, and every time I cut, I'm writing down the node. So I've just gone round, H. Right, now I've got a little bit of time where I'm not, because I'm on the left hand side of all the branches, so I'm not cutting anything. So I should only be writing things down when I'm travelling up the right hand side of a branch, as a double check for yourself. And you will always finish with the root node, unless you accidentally didn't go anti-clockwise. Okay? So, easy as pie. The algorithm is actually quite important, and you might get asked to quote the algorithm in either paper as well, because it's to do with data structures, trees, but it is also to do with algorithms, so it's one of those weird questions. Okay, so that is all you need to remember. You don't have to, in the specification, it doesn't even mention the other orderings, because we've removed the context. And the context was expression trees in compilers. But hey. Right, okay. Oh yes, Colin, go on.
So, if it was to the right, so when it's 2 going down, that's in order, would it say in order first?
Yeah, it would, but they're not going to ask you to do it. So yeah, in the middle would give you in order traversal.
So that's what it's saying.
Yeah. No. It's to do with this. I'll just give you the context. When we write things, we write like this. We write expressions A plus B. Because that's how we work. We're humans. We like to triple and quadruple scan everything before we do things. Computers don't like doing that. They don't like parsing things multiple times. They'd rather do it in one hit. So that is what we call infix. The operation is in between the operands. Computers prefer data like this. And this is what we call postfix, where by the time we do our calculation, we know what data to calculate with. We've seen the data already. With our human version, we've still got to look what's after the B. What's after the plus. So we're still scanning to say what are we adding on to A. With the computer version, we've gone, oh, A and B, what are we doing to them? Oh, adding. You can generate machine code from AV+, dead easy. Okay? Prefix just looks like this. That's prefix. So, again, you can generate machine code quite easily from that because you've got your instruction and then your data. Whereas the human form is just a mess. The way humans do everything is a total load of old junk. Makes it really difficult for a computer. Okay? But that's the context, and the context went. So I do apologise for that. Right, okay, the next bit, adding data to a ordered tree. Obviously, quite important to follow the order of the tree. And it is just effectively, what you're doing is binary searching the tree. Okay, so you decide whether you go left and right. So let's just follow this through. So we've got A first. So we're looking for a branch to hang A off. And we're looking for where a branch doesn't exist. Okay? So we start always with the root. And we look at the root value. If there is no root, then we've just found where we're adding our item to the tree. And the tree points to our new item. But here we have got a partial tree already. So we'll say A. A, is it less than or greater than L? It's less than. So we're doing a binary search because we're actually discarding half the tree. We're saying, oh, don't bother looking at the right-hand side of this tree. Waste of time. So we say, right, follow the left branch. We get to H and we go, A, is it less than or greater than H? Well, it's less than, so follow the left branch. We get to C. Is A greater than or less than C? Well, it's less than. So we follow the left branch and we go, oh, hang on a minute, there's no left branch. That's where we're going to put A then. So we do that. And we put A as clearly as we can. We then do the same with X. So we say X and compare with the root. X is bigger, follow the right branch. T, X is bigger, follow the right branch. V, X is bigger. Now, obviously, I do apologise for using letters at the end of the alphabet to make you have to run through your little rhyme or whatever to remember the alphabet, but I did. You have to write down. That's no shame in that. I always have to go A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. That's the only way I can remember the alphabet. It's stupid. Right, so I get to V, X is bigger than V. Get to Z, Z is less. So Z's got to go left. Now, another thing you must not do. So that's what I've done. Let's explore what some students did. Some students did this. Why is that a sweary problem? It made me swear when I saw these. No, it's not saying left or right, correct. All right, so please, if you end up having to do that because you've squeezed it in your diagram, I would at least go left branch or something. Give somebody a chance to say they are not a donut. They know what they're doing. It's just really badly drawn. I know some of your drawings are appalling. I can see that now. I'm not going to mention names. I have got a little logbook of people not to call to repaint the Sistine Chapel. Right, okay, so the X goes there. Let's do the B. The B's quite interesting. Few people made a mistake on this one. Right, B is less than L. Starting at the root again. Follow the left branch. B is less than H. Follow the left branch. B is less than C. Follow the left branch. B is greater than A. You make a right branch. Okay. Right, final one, R. So R is bigger than L. Follow the right branch. R is less than T, follow the left branch. R is greater than P. That's the only bit I can always start in the middle. O, P, Q, R, S, T. Weird. So it hangs there. That's it. There's nothing hard about that. You should never be asked for an algorithm in the exam, but you will get asked to follow it. Right, the final one. Deletion. Tricky operation in a tree. There's lots of factors in reality that you have to worry about. It's like, what is the effect of promoting one branch over another? Does that leave the tree unbalanced? Right, so in this example, I asked you to promote the S branch when we deleted the root node. So we're getting rid of the root node. So we're saying that you could do it like this. If you want to really do in the examiner, you could go, right, let's move that. Let's say root is there. Let's point root to S. So you could have done that. Scribble that line out. So there's no point there anymore. Although it doesn't matter if there is. And then say, right, okay, so I've promoted the right branch to the root. I need to put the F branch in the correct place. Now the F branch must be to the left. Okay, because it was to the left. So what you're looking for is the smallest value or the leftmost point of the right branch. So that isn't R that's low, it's P. So really, F hangs from the left of P. So you could leave your diagram like that. I wouldn't recommend it. I'm going to use that as my working out, and then I'm going to redraw the diagram. So I'm going to just scroll up a little bit. I'm going to zoom out a little bit so I've got a bit of space. Right, so I have got S connected to U, connected to V down this side. I've got P, which goes from the left of it, R from the right of that. And then I'm hanging the F, the whole subtree, off the left of P. So F goes there, D there, K there. So actually it's not a bad balanced tree after that. That's what you've got to do. If you promote the left branch, what you're then looking for is what is the biggest value in the left branch to hang the other side off. Okay? But yeah, draw your diagram again. You shouldn't have to, but always label up the root node. Just in case someone's being dozy and they look at that. Right, I'll stop there. Anyone got any queries on that one? I think most people got that one.